Great. Thank you very much for having me here today. So yeah, I'm going to talk about, I guess, lower temperature shallow geothermal and a research and innovation infrastructure that's been developed in Glasgow in Scotland. So the observatory that we have in Scotland is around mine water geothermal, both heat, cool and thermal storage. And this is an area that there are a number of proved schemes that are used for heating buildings, both homes and businesses. They're used for heat abstraction, they're used for thermal storage, and for the balance of those two things, supplying heat networks. So we know that it is an achievable thing to do, but there are still a lot of questions about making this a sustainable resource, to increasing the number of schemes and so on that are based around this kind of fundamental scientific processes in the subsurface around sort of heat and flow transfer. So there are questions like, what happens if lots of people start doing this? How sustainable is the resource? How long will it last? In particular, for the economic development of this, the cost and the risk of unsuccessful boreholes, for example, needs to be decreased for it to be rolled out more widely. So as part of that, the UK government invested money in this research and innovation infrastructure in Glasgow. There are some pictures on the screen here of what the observatory looks like at the surface, obviously. So it's specifically focused on shallow mine water geothermal and also the kind of wider urban environmental change. And I'll just talk through a little bit of what's on this slide. So you can see on the bottom left-hand corner, this is one of the research compounds. So in the bottom left of this slide, you can see the label GGA01. That's one of the boreholes that's got a geothermal wellhead. And then there's another 2 boreholes on each site, which are beneath manhole covers, so it's more difficult to see. You can see on this image that there is a heat center and a heat pump chiller towards the top of that photograph. And then the other things on this image are all the monitoring equipment that goes around the site. So that's both at the surface in terms of things like scanning lasers for near surface air quality, and the cabinets we've got for distributed temperature sensing cables, fiber optic cables that are down the boreholes, and electrical resistivity tomography cables also down the boreholes, and all the kind of normal hydrogeological monitoring. On the right-hand side, the 2 photographs are what the heat center looks like in the inside with all its pipes and its heat exchangers and so on. And at the top, the geothermal wellhead and some of the sensors, the pressure and temperature sensors, for example, that are on there. So it's an extremely well characterized site. This is a photograph of where it sits in the kind of wider landscape. So as you can see from the photograph, the small symbols in the sort of middle of the photograph, they're the borehole locations. There are 12 boreholes. The deepest is 200 meters, and that's the seismic monitoring borehole. And the other ones penetrate mine workings that are either at about 85 meters or at about 50 meters deep. The subsequent slides that I will show you focuses on the 9 boreholes that are in the sort of central triangle of this image. But what you can see from this photograph is that the site is located in an urban area, which is both housing and industry in the East End of Glasgow. So it's a really representative setting of what in the UK is an industrial legacy of former coal mining and heavy industry. But it's an area where there is real demand for these for the heat, for low temperature heat. And so this infrastructure essentially replicates what would be a small mine water energy scheme. So this next diagram is a kind of cartoon of what the infrastructure is like. It's not to scale. So for example, the heat center with its heat exchangers and the heat pump chiller are drawn much bigger than the underground infrastructure. But essentially you can see in this image that there are boreholes that are drilled into these mine workings, which are the grey horizontal lines on the image, that are at different depths. And the boreholes are fitted with, some of them are fitted with submersible pumps, and they're linked by a mine water pipe, which goes to the heat centre. And the kind of capacity is that we can pump up to about 12 litres a second from one mine working and into another mine working, or between the same mine working. And what the facility enables is that we can do either heating or cooling of that mine water to then study the subsurface responses, well, and the responses of the surface infrastructure. So on this slide, if you look at the image on the left-hand side, first of all, this is, imagine we were mimicking heating a building. So what we do in this case, we would pump water out of one of the boreholes, and that mine water is about 12 degrees C, so it's not hot by any means, it's just warm. But then that water, it goes through the heat exchangers, and the heat pump chiller simulates that heat user by taking heat out of the mine water. So we might remove about 4 degrees centigrade, and then that mine water is returned to a different level of the mine working where it's cooler. And similarly in cooling mode, this is mimicking maybe what you would do in the summertime. A similar principle, you might abstract water at say 12, take it through the heat centre where you would add heat to the water and inject it into the subsurface. So the slide that I've got here is just an example of some of the monitoring that is in place around the observatory, and I've chosen the temperature example. This is from an experiment that we did during commissioning of the site in 2023, and what it records is the temperature down the fibre optic cable. So if first of all you look at the graph in the middle of the slide, I'll explain what this is. So going down the y-axis is the depth down the borehole, so that goes down to 51 meters, and across the bottom on the x-axis is the time, so you can see there the dates in June. And the colours represent the temperature measured by the fibre optic cables. So you can see before the start of the experiment, this was the kind of baseline temperature of the mine water and the rock. And then this was a thermal storage experiment. So we were putting heat into the borehole. And so you can see that very clearly when the heat was put into the borehole, the temperatures changed, and in particular at the screen section of the borehole, which was down at the mine working, we can see that heat pulse going into the mine working. And then after 24 hours for this commissioning test, the heat was switched off, and we can see the recovery of that. And actually what we can see in the recovery is the influence of the different rock lithologies within this borehole, where there are some lower thermal conductivity zones, which relate to clays and mudstones. And we can see the heat gradually decaying in the mine working. This is an example of the borehole log in this particular borehole. And we can see similar effects on the plot on the left-hand side, which is individual kind of times of the temperature variation. So we've got the baseline geothermal gradient temperature profile down the borehole. The solid lines are when the experiment was active, when there was active pumping, so we can see the increase in temperature. And then the dashed lines are when the experiment is ended, and we can see the recovery of temperature. And so these were just initial commissioning experiments, but hopefully you can see from the kind of data collected, what it's going to enable researchers to do is to really quantify the magnitude, extent, timescale and so on of heat and flow processes in the subsurface that affect the economics and the sustainability of mine water heat resources. So just rounding off this short talk on this final slide, I thought I'd just summarise some of the kind of capabilities that exist at this particular observatory. And in terms of the focus of this group, I mean, it's multi-scale in that we have the original rock samples, for example, from when we were drilling, and then clearly the experimentation goes from a number of different scales up to that kind of big field scale of a few hundred meters. But there's capabilities in terms of the kind of resources and sustainability of resources. but we've also got a lot of monitoring equipment in place, which is listed on the box on the right-hand side. So we've done a lot of sampling and so on of the groundwater hydrogeology and chemistry, the adjacent surface water chemistry, the soil gas profiles, for example. There's some seismic monitoring in place. We've got ground motion, as well as the cables that I mentioned down the boreholes, the resistivity tomography and the distributed temperature sensing, which can also be used in DAS mode. So there's a lot there that can be done to look at environmental change and impacts. The surface infrastructure can be used to look at kind of the operational efficiency of these mine water heat schemes. And it's an infrastructure that's open for people to come and use, so they can come and test their own sensors and so on. So that's really the main thrust of the presentation, just to say that the facility is there. It's available for people to come and use. It's open for anybody to come and use who has a particular either sort of science research question or applied uses. It does have access, transnational access funding through the RISE Energy programme, which is just starting. So there is possibility for EU researchers to apply for that to come to use the observatory, which we're really excited about. And just before I finish, I'm just going to very quickly mention the sort of sister observatory, the other observatory in this cluster, which is in Cheshire and is looking at aquifer thermal energy storage. It's in final commissioning stages with 2,100-metre deep boreholes, and it will open later in 2024. Thanks very much.